Okay, what I want to do in this screencast is go over the problems from Wiki, the last one that we did in class, which we were not able to discuss because the students never claimed those. So let's go over those one at a time. One of the Wikis states the following, it provides the following problems. You're supposed to complete what the major product is going to go in the box. So recall from what I told you, anytime I give you a box type problem which says fill in the blank, I'm seeking the final major product. You can work on the mechanism or whatever you want to on the side on scratch paper, but the box should contain the final product. All right. So the way you should think about this is that there is a positive on the hydrogen, there is a negative on the Br. Of course, your double bond is going to act as a source of electrons, so that's the nucleophile. It's going to pick up the proton. Bromine then would leave, and the carbocation that you're going to get, hopefully everybody can see, according to the Markovnikov's rule, it's going to be the more stable tertiary carbocation, which is where the Br is going to attack, and then your final product should look like H on the carbon which holds more number of hydrogen atoms, and Br on that carbon which is more substituted. If you follow the same principle, the same rule, hopefully you can see that the second one is going to give you a tertiary carbocation. And like I have said in the past, always ask yourself whether that is the most stable carbocation or not. And so you might have thought that, let me just draw the carbocation outside. You might have thought that the carbocation might go through, some kind of hydride shift or something like that, in which case you would want to bring the hydrogen. You don't want to put two positive charges like that, but if you wanted to shift, let's say, that hydrogen over to this position, that will give you another tertiary carbocation. So it's not that you're going to achieve anything, all right? And so for that reason, you can just live with the carbocation that you have. That is a tertiary carbocation. You don't have to go through a shift or anything, and simply show the addition of the Br, and that will give you your product like that. Okay, next question is draw the products of each of the following transformations shown by the fishhook notation. So the fact that it's a fishhook notation should tell you that this is a homolytic cleavage, and so the products should be, this is an initiation, you don't have any free radicals. You're going to end up with a free radical over here and a free radical on the other side. So two of those, and you may write that as 2 and then the tertiary free radical, that's okay too. But as long as you're showing free radicals at the end of the day to signify that it's a homolytic cleavage, and this is an initiation step because we did not have any free radicals on the reactant side, but we do have free radicals on the product side. That will be your product. Okay, let's go forward. The next question asks you to again determine what the products would be when the following combination occurs. So notice in this case, the pi system is forming, is going through a free radical reaction. So you have two methyls here and one of the carbons. So each of the carbons is getting its free radical back. One of the carbons, the terminal one, is going to react with the bromine free radical and it's going to form the bond. And so what your product is going to be is a free radical again. So this is kind of like a propagation step. Propagation. Because you have a free radical in the beginning. There should be 2 electrons over here to denote all the 7 electrons, and you're going to end up with another free radical. So free radical in the beginning, free radical as the product, that's a propagation step. The first example that we did, no free radicals in the reactant, free radicals in the product, that was the initiation step. And the opposite of that, where you have free radicals on the reactant side and no free radicals on the product side, will be the termination step. So keep those three in mind. Sometimes you might just be asked to identify or, which step of the sequence is it. Next question says indicates whether each of the following reactions is homolytic, heterolytic, and you have to explain how do you know that. Write the appropriate fishhook or the curved arrow notation. So they are basically asking whether it's a polar reaction or not. So tell me, what are you thinking? You should be thinking what kind of products you have. Homolytic, same product upon lysis. Heterolytic, different products upon lysis. So notice you have a cation, you have an anion coming from HOH. So the difference in the electronegativity does the trick. And since you have a cation and an anion as the product, you would say that this will be a heterolytic cleavage. Heterolytic cleavage, where one of the atoms, in this case oxygen, took away both the electrons, leaving a proton and a hydroxide. The second one, on the other hand, shows you that you have a methoxy free radical, and it's going to abstract one of the hydrogens from the CHOH bond to give you methanol, and you end up with a radical. So you're beginning with a radical, you end up with another radical. Since radicals are in the picture, you will call this a homolytic cleavage. Homolytic cleavage. And if you had to show the electron arrow pushing, this is what you should do. Oh, let's use the eraser. CHOH plus CH3O with a radical. And so this radical is going to abstract, whoa, too big. It's going to abstract the proton. The other electron is going to go on carbon. So it's going to give you CH3, CH with the radical. The OH remains as is. And now you have the CH3OH, which is your product. That's your newly formed product. But the process goes through a homolytic cleavage of the CH bond. Okay, next question is show the complete mechanism to prepare 3-ethyl-3-iodo-pentane. So let's just draw. It's always a good idea to draw what you have. 1, 2, 3, 4, 5. That's a pentane, 3-ethyl, 3-iodo. From 3-ethyl 1-pentene. So 3-ethyl 1-pentene would be 1-pentene, 3-ethyl. And you have to circle the most stable intermediate and provide the structure of the major product. How do we go about it? Now, there are two ways to go about this, and I'll give you both of those. One of them we have obviously talked about. The other, we will be discussing a version of that in the next chapter. So let's get started. What you can do is, hopefully you can see that the double bond is gone. So you obviously need a hydrogen somewhere. And you're adding an I, so you need an HI that needs to be added in this system. Now recall from what we learned in class that HI is a very, very strong acid. So you can't really use HI as is. You will have to use a combination of Ki and H3PO4, which is going to generate K3PO4 and HI. So 3 of Ki will be required in this process. It's a double replacement reaction. And so anytime we need HI, we generate it in C2. And C2 means within the reaction. So now when I treat this with HI, what's going to happen? The nucleophile, which is the double bond, is going to pick up the proton. Iodine is going to leave, so that was negative, and this is positive, delta positive, and delta negative. And you're going to add hydrogen at the primary center and a positive charge will appear at the secondary carbon. Notice that is in vicinity of another position where you have a hydrogen, and if that hydrogen moves as a hydride over to the next position, so if you have, in other words, a 1,2 hydride shift, you are going to end up with a more stable tertiary carbocation. And this is where your I minus is going to attack and give you your product. So that's how you get the product. Now the question was, you had to circle the most stable intermediate. So hopefully you can see that the tertiary carbocation is going to be the most stable one. And the structure of the major product also is going to be the iodine at the tertiary position. Of course, as we discussed in class, you have to think about whether the iodide, because it's a pretty big atom, so iodide, or ion rather, is going to take some time to get to the site of action. And so it's a possibility that the I minus might be able to attack directly at the secondary carbocation, in which case the minor product is going to be the I at the secondary center, like this, and that will be your minor product. Another way that you could have done this would be if you would use what is called as an iodosuccinimide. That usually goes through a free radical reaction. So your starting reaction would abstract NIS. The beauty of this reagent is that it reacts specifically at allylic positions. Allylic halogenation. So it is this position that was going to generate the free radical, and then the I is going to add at that location. And once you have the iodine, you will then end up reducing it with hydrogen and palladium 1 atm, and so you end up with the I. That's another way, another prepare method, not more so a mechanism, because I never ask you for the hydrogenation. It's a pretty simple mechanism. We never usually put that, but you should know that from the perspective of a prepare question. But yeah, those are our two options. All right, let's get started with the next video.